Assalamu alaikum. My name is Muhammad Nauman Shabbir and my presentation topic is Subline interpolation. First of all, I will discuss about the contents of this topic. So first one is history, introduction, Subline interpolation, and in Subline interpolation I will discuss about linear subline with example, quadratic subline with example, cubic subline with example, and then theorem related to subline, advantage and disadvantage of subline interpolation, and in last application. First of all, I will discuss about the history of subline interpolation. Before computers were used, numerical calculation done hand, although piecewise. Defined function like the sine function or step function were used. Polynomials were generally preferred because they were easier to work with, though the advent of computer subline have gained the importance. It is commonly accepted that the first mathematical reference to the sublines is the 1946 paper by Schoenberg, which is probably the first place that the word subline is used in connection with smooth piecewise polynomial approximate. However, the ideas have their roots in the aircraft and shipbuilding industries. In the foreword to Bertels 1987, Robin Forrest describes lofting, a technique used in the British aircraft industry during World War II to construct templates for airplanes by passing thin wooden strips called spline through points laid out on the floor of a large design loft, a technique borrowed from ship hull design. Now I will discuss about the quadratic interpolation. Given data points x0, y0, x1, y1 up to xn minus 1, yn minus 1, fit quadratic subline through the data. This subline are given by f of x is equals to a1 x square plus b1 x plus c1 at the given interval x0 less or equal to x less or equal to x1. The first subline f of x defined at this interval x0 and x1, and then next subline we will fix f of x is equals to a2 x square plus b2 x plus c2 at this interval x1 less or equal to x less or equal to x2, and then continuously the final subline is describes as f of x is equals to a n x square plus b n x plus cn at given interval xn minus 1 less or equal to x less or equal to xn. Now in the next step I will find the all the unknowns like ai, bi and ci, where I is equals to 1 2 3 4 and up to n. Now there is a graph of the quadratic subline. Here some data points x0, y0, x1, y1, x2, y2 and up to xn, yn, where the graph curvy line showed the sublines. The first subline is between x0, y0, x1 and y1, where is a1 x square plus b1 x plus c1, and the second subline is that between x1, y1, x2, y2 is a2 x square plus b2 x plus c2 and so on. Now each quadratic subline goes through two consecutive data points. As we know that every quadratic subline goes through the two consecutive data points, so here is the first subline describes as below: a1 x naught square plus b1 x naught plus c1 is equals to f of x naught, and a1 x square x1 square plus b1 x1 plus c1 is equals to f of x1, and continuously ai xi minus 1 square plus bi xi minus 1 plus ci minus 1 is equals to f of xi minus 1, and ai xi square plus bi xi plus ci is equals to f of xi. These condition gives us two n equations, and next one is a n x n minus 1 square plus b n x n minus 1 plus c n minus 1 is equals to f of x n minus 1, and a n x n square plus b n x n plus c n is equals to f of x n. Now the next step is the first derivative of two quadratic spline are continuous at the interior points. This is very important point. The two quadratic splines are continuous. First derivative is continuous at the interior points. For example, the derivative of first spline is that, as we know that a first spline is a1x square plus b1x plus c1, and their derivative is that 2a1x plus b1, and the two are equal at x is equals to x1. When we the next condition is we get equal, we are both, now we equal both at x is equals to x1, giving which is equals to, we get 2a1 x1 plus b1 is equals to 2a2 x1 plus b2. Then we rearrange and getting 2a1 x1 plus b1 minus 2a2 x1 minus b2 is equals to 0. Similarly, at other interior points, we get 2a2 x2 plus b2 minus 2a3 x2 minus b3 which is equals to 0, and then 2ai xi plus bi minus 2ai plus 1 xi minus bi plus 1 is equals to 0, and so on to a n minus 1 x n minus 1 plus b n minus 1 minus 2 a n x n minus 1 minus b n is equals to 0. We have n minus 1 such equations. The total number of equation is 2n, which we get earlier, plus n minus 1 which is equals to 3n minus 1. We can assume that first spline is linear. This is very important point. The first spline we consider as equal to 0. a1 is equal to 0, thus gives us 3n equations and 3n unknowns. Once we find the 3n constants, we can find the function at any value of x using these splines. Now I will discuss the example of quadratic spline. The upward velocity of a rocket is given as a function of time using quadratic splines. First one, we find the velocity at t is equals to 16 seconds. Then we find the acceleration at t is equals to 16 seconds. The solution is that the given data is that time at 0, velocity is 0. Time at 10 seconds, the velocity of rocket is 227.04, and so on. The given data is shown on screen. Next, in the next step, we define the splines at the given data. V of t is equals to a1 t square plus b1 t plus c1 at interval 0 is less than t is less than 10. Because the splines defines between 2 points, consecutive points, so we define the first spline at interval 0 and 10. Then a2t square plus b2t plus c2 which is defined at interval 10 less or equal to t less or equal to 15, and a3t square plus b3t plus c3 defines at 15 less or equal to t less or equal to 20, and so on a5. Each spline goes through two consecutive data points, so we defines above splines at the two consecutive data points. V of t is equals to a1 t square plus b1 t plus c1 at 0 10 closed interval. So first we put 0 in first spline, and then we put 10 in first spline, and getting the new equations as a1 0 square plus b1 0 plus c1 is equals to 0, a1 10 square plus b1 10 plus c1 is equals to 227.04. This is the two consecutive data points supplying is given, and then a2 10 square plus b2 10 plus c2 is equals to 227.04, and a2 into 15 square plus b2 into 15 plus c2 is equals to 362.78. And all these sublines are defined at the given two consecutive data points and getting the equations. Now derivatives are continuous at interior data points, as since we know that v of t is equals to a1 t square plus b1 t plus c1 defines at interval 0 and 10, and a2 t square plus b2 t plus c2 defines at 10 less or equal t less or equal to 15. So here we will first find the derivative, and both are equal at t is equals to 10, and getting the equation 2a1 into 10 plus b1 is equals to 2a2 into 10 plus b2, and we put this both sides equal to 0. 20a1 plus b1 minus 20a2 minus b2 is equals to 0, and then we defines at all the data points t is equals to 10, we get this equation, and t is equals to 15, we get a corresponding equation t is equals to 20. T is equals to 20, we get this equation corresponding t is equals to 22.5, we getting the equation. And as we know that the first subline is goes to 0, so a1 is equals to 0, and we set all the unknowns in a matrix forms and their constants, and we find all the unknowns by Gauss elimination method. By solving the matrix by a Gauss elimination method, we finds the coefficients of subline as ai, bi, ci, and I is equals to 1 to 4. So when a1 is equals to 0, b1 is equals to 22.704, and c1 is equals to 0, and a2 is equals to 0.888, b2 is equals to 4.928, and c2 is equals to 88.88, and so on a3, b3, c3, and a4, b4, and c4. Now the final solution is that we putting all the unknown values which we find above as v of t is equals to 22.704t at given interval 0 is less or equal to t is less or equal to 10, and next one is 0.888 t square plus 4.928 t plus 88.88 at given interval 10 is less or equal to t is less or equal to 15, and so on. Now first one we find velocity at t is equals to 16. So this one is equal v of t is equals to minus 0.1356 t square plus 35.66 t minus 146.61 at given interval 15 less or equal to t is less or equal to 20. Oh, this is very important point. Here we find the velocity at t is equal to 16, so we only discuss about the subline which is lie between 15 less or equal to t is less or 20. So we take this subline and putting t is equal to 16 and getting the answer. So v of 16 is equal to 394.24 meter per second square, and then we find the acceleration from velocity profile. The quadratic subline valid at t is equal to 16 is given by as first we take derivative of the velocity profile which is lie between 15 and 20, because we define the acceleration at t is equals to 16. So v of t is equals to minus 0.13560 t square plus 35.66 t minus 146.61. So the acceleration of t is given as by taking the derivative of last spline is equals to minus 0.2718 t square plus 35.66, and then we put t is equals to 16 because we find the acceleration at t is equals to 16. So a into 16 is equals to minus 0.2712 16 square plus 35.66, and a of 16 is equals to 31.321 meter per second square. Now the next example number 2 of quadratic spline is as below. Construct a quadratic spline interpolating through the data points minus 1 0 0 1 and 1 3. So the solution is that assume that the quadratic spline S22 of x is of the form. Let's suppose we assume the splines are as follows. P1 of x is equals to a1 plus b1x plus c1x square on interval minus 1 0, and p2 of x is equals to a2 plus b2 of x plus c1x square at given interval 0 1. Since S22x interpolates the data points, we have p1 of minus 1 equal to a1 minus b1 plus c1, which is equals to 0, and now p1 of 0 which gives this spline is a1 is equals to 1, and when we put 0 in p2 we got a2 is equals to 1, and when we put value 1 in p2 we got a2 plus b2 plus c2 which is equals to 3. In addition, next we find the derivative and equate them. Both splines p1 of 0 equal to p2 of 0 dash gives b1 equal to b2. Above are the 5 linear equations about the 6 unknown coefficients a1 b1 c1 a2 b2 c2 which have infinitely many solutions. If we impose one more constraint, for example s2 n into minus 1 dash which is equals to 0, this implies that b1 minus 2c1 which is equals to 0, then there are 6 linear equations for 6 unknown coefficients from which it can be solved. That when we solve the above all unknowns, we got the unknowns values as a1 is equals to 1, b1 is equals to 2, c1 is equals to 1, a2 is equals to 1, b2 is equals to 2, c2 is equals to 0. Therefore the quadratic spline function we got from this unknowns constants values is equal to 1 plus 2x plus x square. This is the first spline which is defined at minus 1 0 interval, and the next spline is 1 plus 2x 1 plus 2x at the interval 0 1. Now I will discuss about the theorems of spline interpolation. Like theorem 1, a linear spline interpolation is well posed and well conditioned for any node distribution. Applying our error results for the interpolation polynomial to the linear interpolates gives us the following error estimate. Theorem 2, let f belongs to c square ab. Any function which is belongs to c square ab close interval, it says that a function is continuous at second derivative, then norm f minus s n infinity ab closed interval less or equal to 1 over 8 h square maximum norm of f double dash infinity to ab interval, where h maximum is equals to maximum of 0 is less or equal to I is less or equal to n minus 1. where h maximum is equals to maximum of 0 is less or equal to I is less or equal to n minus 1 absolute of xi plus 1 minus xi. Proof: take some arbitrary x belongs to a b closed interval and suppose it lies in the interval xj comma xj plus 1 closed interval. Then since the spline interpolation consists of localized hat functions, since we sum such that f of x minus here sorry to set that here the some values are missing, uh, such that f of x minus Sn x absolute value less or equal to 1 over 2 f double dash of x into x minus xj into x minus xj plus 1 absolute less or which is less or equal to 1 over 8 8 square maximum of f double dash norm infinity at the closed interval xj plus 1. Taking the maximum over all x belongs to ab yields the claim. Now I will discuss about the advantage of spline interpolation, useful for estimating above maximum and below minimum points, creates a smooth surface effects, and the disadvantages of spline interpolation are as below. Cliffs and fault lines are not well presented because of smoothing effect. And number two, when the sample points are close together and have extreme differences in value, spline interpolation does not work as well. This is because spline uses slope calculations, change over distance to figure out the shape of flexible rubber sheet. And now the applications of spline interpolation are: interpolation is helpful whenever you have to scale things up or down. We interpolate the values to all aspects of things to measure. Maybe you know much catering cost for an event. Here is the example: party. Maybe you know much catering cost for an event with 10 people and also people as well as 100 people, but you need an accurate estimate of how much of catering will cost for 25 people or 75. That a useful thing to know just for hosting a nice party. Now the second one is buying a car. uh, um, how much money will you put into a car that has certain number of miles on it? Can you afford it? That's interpolation. And number third is how many gallons will it take to get to a certain place? How many time will you need to fill up? What will that add t to your travel time? That's also the interpolation. Thank you so much.